So this is the last lecture before we start the review session. Before we start this lecture, I'd like to actually ask you for a favor. Namely, please go to your browser and enter uft.me/open-evals. And just take 5 minutes right now to fill out the course evaluations for this course. This helps me a lot for future teaching and as feedback, so that I know what to improve and what has been good. I don't think you can give me stars, to be honest, but if you could give me stars, that would be appreciated. And I'm technically not a professor either, so I'm neither a prof nor do I have 5 stars. I think if you type in uft.me/open-evals, this should work. Wait, let me check 1 second. Yeah, so in my case, it takes you directly to Quarkus, to the tab. I don't know if there's another way of doing this. On the 4th try, okay. Actually, let me know. Check, so if you have. Evals, so it, doesn't seem to be loading, but it worked before. Otherwise, just go to Quarkus. This one. Go to Quarkus. And then on the bottom left, you can see course evaluation. So you can also tap here if the other link doesn't work. My Wi-Fi is just very slow, and I just have one Ethernet cable for the computer. Okay, does anyone need more time? I guess we could wait another 3 or 4 minutes. Are there any questions you want to ask before we start? If you're done with the evals, you can just ask questions. Maybe something from last week, because we're going to dive right in today and finish this discussion of the Jordan canonical form. The last discussion was last week at the end. This example where we computed the generalized eigenspaces, and we then saw that these are actually sufficient to write a to write the vector space as a direct sum of the generalized eigenspaces. And today we're going to use this example and make this more general. So we're going to work towards a theorem that every transformation indeed has a Jordan canonical form, and we're going to see how to compute it. Okay, so actually, when you're done with the evaluation, have a look at this discussion. So this is what we're going to start with today. And if it's not clear what this means, you can always go back to this previous discussion and understand what it means in this case. Because in this case, you have an explicit example, you have a matrix that's given, and you can verify if it holds in this case, and then you can try to prove it more abstractly in this case. So the first one is that when we define the generalized eigenspace, remember that k lambda was the kernel of t minus lambda I to the m, where m is the multiplicity of lambda. And the first thing I wanted to show is that that the only eigenvalue of t when restricted to k lambda is in fact lambda. So there's no other eigenvalue possible. The second one is whether t minus lambda I is nilpotent on k lambda. Remember, intuitively, this just means we subtract the eigenvalues in the diagonal, and then we're going to have upper diagonal matrices. But without just a basis, you can still show this abstractly. And the last one is show that this k lambda is an invariant subspace in T, and I mean this for T. So I'll give you another 5 minutes now for the discussion, or maybe 4 or 5 minutes, and then we'll discuss that. Any questions before about the statements? Is it clear what these all mean? Okay, maybe let's start with the first one. Does someone have an idea of how we can show this? As a hint, it's pretty much brute force. So if you just have any idea, it might be the correct one. So what would it mean for this to have an eigenvalue to begin with? So if you consider T restricted to k lambda, this really is just t, but we only want to consider inputs from k lambda. So if you suppose that has an eigenvalue sigma in R, or I should rather say the field F, then we know that T of V is equal to sigma times V for some V in K lambda. Remember that this was the kernel of T minus lambda I to the M lambda. So now this means that if we apply T minus lambda I M lambda times to V, we should get back 0, just by assuming that it's in the generalized eigenspace. And now if we apply this, we just apply this step by step. So we just reduce the power by 1. And then we have T minus lambda I reply to V 1 time. And then this is the M minus 1 remaining ones. So we just, if you have a successive application of a function, you can just, transformation, you can just apply them 1 by 1. Okay, so then as a next step, well, now we use the fact that we assume it has an eigenvalue sigma, and I didn't say what sigma is. It could be lambda or not lambda. I want to determine that it has to be lambda. Then now I have T minus lambda I still M lambda minus 1 times applied. And here I have TV minus lambda IV, but this is now sigma V minus lambda V. And I can more conveniently write this as T minus lambda I M lambda minus 1 sigma minus V, sigma minus lambda times V. And this was just for the first application of T minus lambda I. Now, if I do this M minus another like M minus 1 times, I get another factor of this. So every application of this transformation gives me a factor of sigma minus lambda. So in the end, I have sigma minus lambda M lambda times V. And now from this equation, you can see that this has to be 0. So this is 0. Only if sigma minus lambda is 0, so sigma is lambda. So any eigenvalue has to be lambda. It can't be anything else. We do assume here that V is non-zero, but this is just coming from here that otherwise it wouldn't be an eigenvalue. So what I mean by brute force, I realize that this is longer than you might expect. I didn't say that it was easy, and it's always subjective and dangerous to say that something's easy or not. It's not supposed to be easy, but brute force is a different thing. Brute force means you literally put in the one thing you know, and you just push it as far as you can, and eventually you get to the goal. So there was 2 things that I know in you. I restricted to k lambda, so I know that it has to be the eigenvalue the eigenvector has to be in k lambda. That's what gives me this thing, and I know it has to have an eigenvalue. This was the other thing. So I only put in 2 things that I knew, and I just try to see where this leads me. Okay, so the second one is indeed shorter. Any ideas why T minus lambda I is nilpotent when restricted to k lambda? This is almost tautological. So there's not much work. It's just a matter of like seeing it the right way. And again, T restricted to k lambda just is the same as T same as t going from v to v, only consider inputs t k lambda of v for v in k lambda. So that's the idea for the restriction, as I think I explained last week. I'm not sure what you mean by your comment, Adrian.
Just because we know like there must be some vectors, like some generalized eigen vectors. Instance,
so what we want, remember that nilpotent means that t restricted to k lambda to some power, say n, is equal to 0. And this means that this is 0 t restricted to k lambda to the n of v is 0 for all possible inputs. But now the possible inputs are exactly in the kernel of some power of this. Oh, sorry, I actually, sorry, I wrote something wrong. We're not talking about t itself, we'll be talking about t minus lambda I. So this has to be nilpotent. But nilpotent means some power of it is 0. But if you restrict the domain of this to be k lambda, and k lambda is defined to be the kernel of this map to a certain power, then it is clear that, let me erase this. Now, by definition, t minus lambda I to the m lambda v is equal to 0 if v is in k lambda, because it's the kernel of t minus lambda I to the m lambda. So at the latest, when it's the power m lambda, then we know that t lambda I v is equal to 0. It's not true for the whole vector space. So it's important. It's enough to check these vectors in the generalized subspace because we restrict this. So this is the reason why it's nilpotent when restricted to k lambda, but not on v. So maybe t minus lambda I not nilpotent on all of v. Any questions? I mean, all I just said is it's true by definition, but you have to really, there's not much more I can say. But it's just a matter of seeing it the right way. Like it has to be the right perspective. If there are questions, I can repeat myself, but if not, then I feel like I'm just repeating myself for no reason. And I don't know how to repeat myself differently. Okay, cool. Otherwise, if there's like questions, you can also ask me in the office hours. So the last one is probably the most interesting one. Then we have to show that k lambda is an invariant subspace. What does that mean? Well, it means that if v is in k lambda, then t of v is also in k lambda. So what does this mean? We want to show that t minus lambda I to the m lambda sends it to 0 because it's a kernel, and we want to say it's in the kernel again. So we just apply this. This is the kind of brute force idea. It's not easy necessarily, but it's brute force. There's only one thing that has to be true, and you just try to, even if you're not sure how this will work out, you don't know that has to be the thing that works out. Okay, so now the question is, we need this to be 0. And then T of V would be in the kernel. Well, notice, and this is somewhat of a trick, that we assume V is in the kernel. So this means to this expression, T minus lambda I to the m lambda TV, without any problem, we can subtract something that is 0. So we just subtract lambda times T minus lambda I to the m lambda of V. This is 0. So it doesn't matter if we add it to the term or not. But now that we've added this, you can see that this is T minus lambda I m lambda TV minus T minus lambda I m to the j lambda times V. So we have the same transformation applied, and we sum them together. And now we use we use the linear transformation property backwards. So we combine two different t of x and t of y to t of x plus y, where the transformation in question is t minus lambda to the m lambda. And then inside the argument, we have now tv minus lambda v. But this turns out to be exactly, we can also rewrite this now. So this is now t minus lambda I applied to v. And so we see that this is the same term as the one in the front. So in total, we can summarize this as t minus lambda I, and now we have m lambda, the m lambda plus first power of this applied to v. And this is 0 by the assumption that v is in the kernel of t minus lambda I to the m lambda. So what we've shown in conclusion is that tv is in k lambda, this kernel. Okay, any questions? The only really idea here that you need to put in is that you're able to add a term that's 0, but you still want to add this because it extends the term to have a nice form that you could combine it with the first one. So the last step follows. Do you mean this one? So maybe I could I could make a step in between. So the step in between is now that this is t minus lambda I to the m lambda applied to t minus lambda I applied to v. So if you apply this m times and then another time, it's the same thing applied m plus 1 times. And then because so then you could technically change the order. So you could put t minus lambda I here, and then you would have this in front. But if this is 0, then the whole thing is 0, because transformation sends everything that's 0 to 0 again. And we know that this term is 0 because v is in the kernel of this. The same answer is true for Johan's question. We know that this term is 0 by assumption that oh no, not this one. That v is in the kernel to begin with. And this is exactly what it's the kernel of. So k lambda is the kernel of this this transformation. Does that make sense? Okay, perfect. So okay, so now that we got these kind of exercises or these lemmas that we need for the proof out of the way for the final proof. Well, actually, there's not the preliminary result. Let's look at this discussion, proposition. And this is actually a proposition from the book. So the book states this. And this is the preparation, the final thing we need to state the theorem in a minute. So the first thing that we always need to assume is that the characteristic polynomial has enough eigenvalues, and this is true if f is algebraically closed. It might also be true for non-algebraically closed fields if the transformation is nice enough, but it's certainly true if f is algebraically closed. So for example, for C. Okay, so then the first thing we've already shown in this discussion above is that the invariant, the generalized eigenspaces are indeed invariant subspaces. The next step is to show that we can actually write the vector space V as a direct sum of these generalized eigenspaces. And the third assertion that this proposition makes is that each eigenspace has a dimension which is the multiplicity of the eigenvalue. Compare this maybe. So this is interesting because compare this to the dimension of the eigenspace. The usual eigenspace is less or equal than m lambda. But the generalized eigenspace always has the right dimension. So and this was really the obstruction to being diagonalizable. And now the goal of this whole discussion is how can we find a canonical form that is never obstructed? So there's never a problem of getting this null form. Okay, so the proof of the first one is already done above. The second one, I don't want to give you all the details. But basically, the way that you can show this you can show recursively that first for an eigenvalue lambda of t on V, you can write V as k lambda plus the image of t minus lambda I to the m lambda. So really, this is just the kernel of the same thing. And we can say that by the dimension theorem, we know that the dimension of V is equal to the dimension of the kernel of this beast here. Let me just maybe give this a name. Let me call this stars. I don't want to write this out all the time. So the kernel of this and the dimension of the image of this will sum directly to the dimension of V, because it's a transformation on V. And then let me just say this as an exercise. So the exercise that you would have to do to complete the proof, there will be 2 or 3 exercises here. Exercise 1 is to show that dimension of this intersect the kernel of this is 0. So this would justify that this is actually direct sum. Okay, and then the next step. Now that we have decomposed V into 2 subspaces, and maybe exercise number 2. The image of T minus lambda I to the M lambda is also invariant. This is really this is very similar to showing that the kernel is invariant. It's a very similar idea, and I'm happy to go over this in the office hours. But right now, I'll just pose this as an exercise. So now we've been able to divide the vector space into one general subspace and the rest, the leftover. So now this means that T on V can be written as T restricted to K lambda plus T restricted to the image of T minus lambda I to the M. So then another, this is the final the third exercise that we'd have to like fill in for this proof. We've seen that this has only eigenvalue lambda. And so exercise number 3 would be to show that this has only eigenvalues not equal to lambda. So they can have any eigenvalues but lambda. And then if we continue this, so then continue or repeat this to finally we can get that V is indeed K lambda 1 plus K lambda 2 and so on, K lambda K. And the reason is if you have eigenvalues, so if you assume that the coercive polynomial of T on V has eigenvalues, enough eigenvalues, namely dim V eigenvalues, then you also know that this one has eigenvalues. And then so you just treat this as a new transformation on a new vector space. And again, the eigenvalues will have some general eigenspace. And then you can divide this again into K lambda and the image. But really what we get is in the end, we get a decomposition of V. And this is really what, this was the goal. And then And then the third step is a consequence of the second step. So if we compute that CT of the classical polynomial of t restricted to k lambda 1 of lambda, this only has one eigenvalue. That's what we showed in the discussion previously. So only eigenvalue lambda 1. So this is this is lambda minus lambda 1 to the dimension of k lambda 1. And so this means that the multiplicity CT of lambda on all of V is lambda minus lambda 1 to the dimension k lambda 1 times times the characteristic polynomial of t restricted to the image of t minus lambda I to the m of lambda. So this means that the multiplicity of lambda 1 is at least the dimension of k lambda 1. But if moreover, if lambda 1 is not a root of CT restricted to image t minus lambda I to the m, which was the exercise number 3, that the restriction of t to the other space, not the general eigenspace, does not have any eigenvalue equal to lambda. Then we know that there's not going to be another factor of lambda minus lambda I. So we know that that m lambda 1 is exactly indeed dimension of k lambda 1. Any questions? Okay, so now we're ready to state the final theorem. And then the only thing follows are two discussions of hopefully which we can do one, and then maybe we'll have the other one in the review session. So the final theorem of this section is that any linear transformation on a finite dimensional vector space such that it has enough eigenvalues, namely dim v many eigenvalues, first of all has a canonical basis. And canonical means that the Jordan matrix of this transformation in this basis has Jordan canonical form. And we defined last week what this form means. It's basically just a direct sum of Jordan blocks. And the second statement is that its decomposition is unique. So there's only up to reordering of the Jordan blocks, which means just you commute the elements in the basis. There's just one unique decomposition. And the proof now is really just putting together all the building blocks from before. So first one from the above, and this might just be a sketch, and don't want to be overly careful right now. Well, first of all, we decompose V into these generalized eigenspaces. We know from above that they're invariant, and we also know that on k lambda I, t minus lambda I is nilpotent. And this nilpotency really, let me call this Ni. There's a basis, or there's a canonical basis for, oh, sorry, forgot to mute. Canonical basis for Ni, in which T, which is nothing but, so T restricted to K lambda I, which is Ni plus lambda I. So if this is nilpotent, this is then canonical nilpotent form, then if you add the diagonals, the lambdas on the diagonal, then this is a Jordan block. And then the second step really is, so this is really high level. So this is not anything deep or technical. It's just using the fact that we've spent like a week on finding canonical basis for nilpotent transformation. So now that we have this, well, we just make a basis, construct a basis for V from the canonical basis of K lambda 1 to K lambda K. And if you take a union of bases, then of course what we need to know is that this is still a basis, because we would still want this to be independent. It has to span the vector space, but this is already taken care of in these propositions, because we know that if we have a direct sum of two subspaces and we have bases of these subspaces, then the union will be a basis of the direct sum of these subspaces. And check that in this basis, T has or is in canonical Jordan form. I don't think the book is more detailed either. But if you maybe it would be good if you look in the book and just see if they have a different approach, if they maybe have more details. Why is it linear independent? It's a good question. Well, this follows that. So maybe let me make this it's a new star. So if W intersect U in V is 0, then you can definitely show that. I'm pretty sure that then W in W and U in U, this means that W and U is independent. We had also some proposition to this effect. So we did do this before. We did take unions of bases of subspaces which intersect trivially, so which are disjoint. But basically just check if you take any combinations. If you take alpha w plus beta u is equal to 0, then you can find some contradiction. Maybe I'll spend time in office hours in a second on this. Okay, so the last 3 minutes plus maybe 2 minutes extra, I want to focus on this discussion because this really gives you a good intuition of the steps necessary to find the canonical form. Unfortunately, there's no time for you to think about this yourself, but maybe let's just look at this together and work through this together in the last remaining minutes. Okay, so you're given a transformation on a vector space V, and let's assume that this is the cursive polynomial, and also that the dimension. So this is probably important. I forgot to write this. The dimension of V is supposed to be exactly 8, so that this actually has as many eigenvalues as the dimension of V. And now we would like to find the canonical Jordan form of this transformation. So what would be the first step that we need to take to find this Jordan form? Yeah, the theorem is very important now. So rather the proof. So rather the proof of how to find this. Any ideas of how to find this? Yes, Jordan has a good idea. Only eigenspaces are not helpful anymore because now we're talking about generalized eigenspaces, but maybe you meant that anyways. So we need to build Jordan form from blocks, i.e. T restricted to K lambda I. Now the question is, what are those? And well, the construction of the proof, the proof is really constructive because it says these Jordan blocks are really just T restricted to the generalized eigenspaces. And so when we let's start with K1. So K1 is the kernel of T minus 1, so T plus I to the 4, because lambda 1, the first eigenvalue has multiplicity 4. And so when we restrict to T, well, we really want T plus I restricted to K1 or yeah, K1 is nilpotent. Now the question is, what is the tableau of its canonical basis? Well, we know we had an exercise to compute this, and this really is that. Let me just remind you. It says that the jth column of this tableau has kernel T plus I restricted to k1 to the j minus kernel t plus I restricted to k1 j plus 1 columns. So there's one additional information that we need, otherwise we can't solve this. We need to know that the dimension of the eigenspace of this is 2. So this means from the statement, we know that the kernel of t minus 1i, which happens to be just the usual eigenspace, which is t minus 1, has dimension 2. This is the assumption that we put in. So this is part of the statement. This is the first thing we know. And the second one we know is that the kernel of t plus I to the 2 is all of k, k minus 1. This has dimension dim k minus 1, which is m minus 1, which is 4. So step by step, we can extract all the information we need in order to know that the tableau has to have the form. I mean, it's 2 columns in the first 2 boxes in the first column, and then 4 minus 2 column boxes in the second column. So it looks like this. Yeah, it's right here. It says the dimension of the eigenspaces are 1, 2, and 1. Okay, so I noticed that it's already 4 minutes past 4, and we still have discussion. We have 2 hours of discussion tomorrow. In case someone needs to leave, I'm going to continue this now, but I'll repeat everything that I say from now on tomorrow. So that if you have to go, then please feel free to go. I'll let the recording rolling because maybe you want to also see this in the video. But this is the end of the lecture for now. There's only this discussion and another discussion that I wanted to talk about, but I'll just include these in the review session tomorrow. And the overall plan for tomorrow is that we have 2 hours left in which I will pose as many questions and discussions that I can think of about all the material from this semester. And with that, I hope that we can cover a lot of things from the semester and review them. I don't think it's very productive if I just repeat myself saying things that we used to have, but if you're actually actively thinking about discussion problems, then maybe we'll be able to cover more, and you'll notice what you should review and what you're comfortable with. Any questions before I end the lecture? Before you go? Okay, then I'll see you tomorrow. And for now, I'll just continue with this and then naturally continue to my office hours. Okay, so where were we? So this was a bit fast, I guess, but basically I did tell you that we want to find the generalized eigenspaces and then the canonical forms of the nilpotent mappings that we get by restricting T minus lambda I to the generalized eigenspaces. Okay, so we got the first block. And this means that there's some basis on k minus 1 such that T And remember, this is now ni, t restricted to k minus 1, which is n minus 1 plus minus 1i, has basis minus 1, minus 1, 1. This is the first Jordan block. And then we have another minus 1 and minus 1. This is the second Jordan block with the 1. And these Jordan blocks really they correspond to the cycles. So this is the alpha 1 cycle, and this is the alpha 2 cycle. And these were the alpha 1 and alpha 2. Yes, Adrian, you have a question.
Yeah, so just before we found the tableau.
I can't hear you. Are you unmuted?
Oh, I think I am. Can you hear me now?
Oh, I think I have oh boy, is that? Yeah, I changed my setup a little bit. That was a mistake.
Oh, okay.
Let me just ignore these now. Okay, can you?
Okay, yeah, so just before we found the tableau, I was just wondering, because we said the kernel of t plus I squared is equal to k of minus 1, but shouldn't it be k of t plus I to the 4? So I'm a little confused for that part. Because we said like the multiplicity of k minus 1 was 4, so I thought it would be that the kernel of t plus I to the 4 would be equal to k minus 1.
Oh yes, but that's correct. We already know. So the last point here that we were given says that when t plus I is restricted to k minus 1, then everything is 0. So this literally means that everything in k minus 1 is set to 0. And this means everything in k minus 1 is in the kernel of t minus t plus I restricted to k minus 1.
Okay, oh, that makes sense. Oh, I didn't see the third assumption there, yeah.
Okay.
Okay, next.
Okay, so basically, I just want to finish this before we go to my office over to my office hours. Any questions for the first tableau and the first canonical form so for now? Basically, this is the first iteration of finding a canonical form for your protein mapping, and then we repeat this for the second one. So now the same for repeat for k. What was the second eigenvalue? Second eigenvalue is 2. Wait, why did I start with 2? Okay, so now let's do this for 2. So k2. This is the kernel of t minus 2i to the multiplicity of the eigenvalue 2. The multiplicity, as you can see here, is 3. So the question is, what is the tableau of t minus 2i when restricted to k2? And what we need to compute is the kernels of the powers. So we need to have the kernel of t minus 2i to the 1, kernel of t minus 2i squared, and kernel of t minus, actually no, I can already put it back in. And t minus 2i to the 3. So these are the pieces we need to deduce from the statement. Well, t minus 2i, this is the first power is always the eigenspace. So this is e minus 2. So the dimension of this is given in the statement. The dimension of the eigenspace of E2 is 1. And the third power, this is the same as the dimension of K2, because this is just, if the power is the multiplicity of the eigenvalue, then this is just the generalized eigenspace. And we know from the proposition before, it was a proposition before, that this is just the multiplicity of 2, which is 3. You know, the only question, what is this? So this is the thing that we don't know. But there's only really one possibility, because it has to be increasing from 1 to 3, and it can never be the same as 1 and 3, so it has to be 2. But this is really so there's no other option. And then the tableau just looks like this. And the canonical form, or the Jordan block of t restricted to K2 in this basis that we know that exists. We don't know what it is, but we know that it exists, and we know that the form itself of the matrix doesn't depend on the actual basis. This is going to be one, so it's just one cycle of length 3, and so we know that this is the eigenvalues on the diagonal, which is 2, and then a cycle of length 3. So this whole thing is a cycle. Okay, so lastly, I'm almost done. Way over time, but almost done. I mean, technically, this is my office hours now, so I shouldn't rush. So lastly, repeat this for lambda 3, which was 5. This is very simple now. Lambda 3 is 5. Multiplicity of is 1. So we know that the generalized eigenspace K sub 5 is the same. It's just the dimension of t minus lambda 5i to the 1, but this is the same now as the eigenspace of 5, because if you have just multiplicity 1, the generalized eigenspace and the eigenspace do not differ at all. Okay, and now, well, this means that what did I write here? Kernel. So this means that the kernel, the dimension of the kernel of t minus 5i is just the dimension of K5. This is the multiplicity of 5, and this is 1. And so it is very quick. It's very quick to deduce the tableau of this nilpotent mapping is just one box. There's not much else. And with this, we know that the canonical form of T restricted to K5 is just 5. So this is a 1-by-1 matrix, also known as a number. Oh, there was a question, but I think it was answered. Yes. So the thing that you kind of do first is you from this really a site an intermediate step would be to have this nilpotent canonical form like this, and then you put back in the eigenvalues, and then you have the form that I have here. Okay, so now in total, it's time to wrap this up. We know that V decomposes as K. What the order that they wanted is 2, -1, and 5. 2 plus K of -1 plus K of 5. This is a direct sum decomposition. And at T, the matrix of T in some basis, and this basis really doesn't matter, it's just some basis which is canonical, will be a direct sum of these Jordan blocks. If I remember correctly, the Jordan blocks look like this. Yeah. So this means in total, the Jordan block looks like this. The Jordan form looks like this. We have 2, 2, 2, -1, -1, -1, another -1, and 5. We have 1, 1 here. We have 1 here, a 1 here, and that's it. I can highlight again the boxes. So the cycles we had in total, and that's the reason why I think someone asked before why there is like a 1 missing here, but it depends on what the nilpotent form of the restriction to this generalized subspace is. This is so we had 1 3 cycle, we had two cycles, and we had just this one. Okay, that's the end of the discussion. Any questions, or is that clear? Yeah, I'll stop the recording now.